This video is on function transformations. We're going to do some examples using our general forms of linear, quadratic, square root, and exponential to determine the transformations that are happening to the equations. So we're going to state the parent function and then the transformations of each equation, and then we're going to graph. So the parent functions, we have to know if they're going to be linear, quadratic, square root, or exponential. And there are other parent functions. And then we're going to state the transformations of each equation. Then we're going to graph. You also kind of want to understand that the graphs from the parent functions, the graphs are going to change. And if you can see the change in the parent from the parent functions, it might help you understand what the transformations occurring actually are. This first example, the parent function, if you look at the equation you're given, the symbol on here is an exponent of 1. That means if we take off all of the numbers and just leave the symbol, our parent function would just be y equals x. That's linear. Our parent function, I'm going to graph our parent function in pencil just so that when we graph the equation, we can see what transformations have actually occurred. So my parent function will go through 0, 0, and it will have a positive 1 slope. So I'm just going to very lightly just graph my parent function in pencil. Now we need to determine what values from our general form have been changed. The a value from the original parent function to the new equation has not changed. It is still that positive 1. There is no parentheses on here, so that means that the h value has not changed as well. The k is on the outside. There is a plus 4 on the outside. That tells us that the k has changed, so the k is equal to 4. What has happened is the k is the vertical movement. Positive 4 means it is going up 4. That is the only transformation that is occurring. What that means is that every one of these original coordinates from the parent function is moving up 4. So if I move this parent function, the original coordinate, up 4, 1, 2, 3, 4, and I move every coordinate I can up 4, so I just continue moving over. 1, 2, 3, 4. 1, 2, 3, 4. I can also come down here. 1, 2, 3, 4. I can continue moving these up by 4. The equation y equals x plus 4 is a y-intercept of 4 and a slope of 1. So this is a y-intercept of 4 and a slope of 1 over 1. That means I can continue going down 1 and left 1, and this is still making all of my parent function coordinates move up by 4. 1, 2, 3, 4. 1, 2, 3, 4. They're all just moving up by 4. So our transformation, every single coordinate, not just one, but every single coordinate that we graphed was moved up by 4 because that was the only transformation that occurred. You can still always just graph this normally, how you would normally graph it, and you can see what transformations have occurred. On this next example, if we take off all of the numbers and leave the symbol, we're left with y equals x squared. So the transformations we're looking for from our general form for quadratics, the a. The number in front is a positive 1, but in the equation, a is actually equal to a negative 1. So the 1 stayed the same, but the sign did not. So a is equal to a negative. The parent function does not have parentheses, but this one does. So that means the h value has changed. It's supposed to be x minus h. So it would be x minus a negative 3 in order to get a plus 3. So h is actually equal to a negative 3. Because if I did x minus negative 3, that would turn into plus 3. There is no addition or subtraction on the outside of the parent function, but now there is. That's our k value. Our k is 6. So the transformations that have occurred. First transformation is the a value of a negative reflects this graph over the x-axis. So it reflects over the x-axis. Then it will move left 3 because the h is your horizontal movement. That to the negative 3 is left 3. Then it will move up 6 because that k value is 6. These are your transformations. And again, we can have our parent function graph. So the parent function of a quadratic goes through 0, 0, 1, 1, 2, 4, and then we can actually mirror them. So I can go to negative 1, 1 to negative 2, 4. And I would lightly graph this. This is just the parent function. So what we can do, we can actually create the graph from the parent function using the transformations. We can also just graph this, get the coordinates, and just graph it. But without the use of a calculator, it is still possible. So if I take any coordinate, any of these coordinates, and I reflect over the x-axis, move them left 3, and then up 6, I will have my new coordinate. So to reflect this coordinate over the x-axis, it already is because it's on the x-axis. Then I want to move left 3, 1, 2, 3, and then up 6. 1, 2, 3, 4, 5, 6. This is our new vertex. If I want to take this next coordinate, to reflect over the x-axis, I have to go to the x-axis by counting once, then I have to reflect over by counting one more. This is a reflection. This will just reflect to here. Now I need to move from this coordinate left 3 and up 6. 1, 2, 3. 1, 2, 3, 4, 5, 6. This is my new coordinate. Since you can mirror this over the axis of symmetry, I can do the same thing. This being my vertex, here would be my new axis of symmetry. I can mirror this coordinate to here. So then I can go to this next coordinate and do the same thing. To reflect, 1, 2, 3, 4 to get to the x-axis, and then 1, 2, 3, 4 to reflect. Now I need to move left 3, 1, 2, 3, and then up 6. 1, 2, 3, 4, 5, 6. This is my coordinate. Then I can mirror it across the new axis of symmetry, which is here. So 1, 2, 1, 2. These are the same 5 coordinates used with the transformations. We can always get more coordinates. So I have negative 1, but I might want another coordinate to make it as accurate as possible. So I can always try and find my y-intercept, my new y-intercept, by plugging 0 into here. So I'd have 0 plus 3 is positive 3. 3 squared is 9. Times the negative is negative 9. And then negative 9 plus 6 is a negative 3. So 0, negative 3 is also a coordinate. But then I can mirror that over the new axis of symmetry, which is 1, 2, 3, and then I can do it again. 1, 2, 3. So here's my mirrored coordinate. Now I have enough coordinates to be able to graph this accurately. And again, we always could have just found the coordinates by hand by plugging in numbers like we just did. This is a vertex of negative 3 and positive 6 because your h and k are negative 3 and 6. That's your starting point. That is your vertex. That's using the transformations to help us with our graphing of our parent function coordinates. On this next example, parent function, the symbol is a square root. So if we get rid of the numbers, we have y equals the square root of x. So the transformations, the a, h, and k, we're always looking for the a, h, and k. The a is in front, nothing has changed. The h, nothing was in the parent function, but there's now a negative 2 in here. So the h, to get a minus 2, that'd be x minus a positive 2. So h is equal to a positive 2. There was nothing on the outside of the parent function, and there's nothing on the outside of the new equation. So h equals 2 is the only transformation. That means that it's moving horizontally to 2, which is right 2. The parent function of the square root of x is graphed at 0, 0, 1, 1, and 4, 2. Because I'm taking the square root of 0, square root of 1, square root of 4. The next one would be at 9, 3. So this would be our parent function. And we just want to move these coordinates to the right 2. So this first coordinate is going to move right 2, 1, 2 coordinate. Next one is move right, 1, 2. Next one, 1, 2. Now I have the same 3 coordinates, and I can connect them and have our new function. So this would be 2. So 2 minus 2 is 0. The square root of 0 is 0. 3. 3 minus 2 is 1. The square root of 1 is 1. 6. 6 minus 2 is 4. The square root of 4 is 2. So we know that that is correct. On the next example, if we take off all the numbers except the symbol, we're left with y equals x squared. What's happening from the parent function to the new one? The a value has changed to a positive 2. It was already positive, so it just changed to a 2. And nothing else changed. I still have just that x squared. That tells us that our transformations are a vertical stretch. It's a vertical because it's affecting the y value of the coordinate, and it's a stretch because this is a bigger than 1. This is a dilation, so it's stretching. It's a vertical stretch of 2 because we're going to multiply our y values by 2. There is such thing as a horizontal stretch, which means you will multiply your x values by something. There's also a horizontal compress. So again, I'm going to graph my parent function, so 0, 0, 1, 1, 2, 4, and mirror them. So what we want to do is multiply the y coordinates by 2. So 0 for x, and then the y is 0 times 2 is still 0. So 0, 0 is still our coordinate here. Then this is 1, 1. So the x value of 1 stays the same, but the y value of 1 multiplied by 2 becomes 1, 2. This is my new coordinate for that first one. This one has a x value of 2, but a y value of 4. The y value needs to be multiplied to become 8. So this new coordinate would be 2, 8. So I need to come up. It'll come off the graph. I do want to plot that. That'd be 2, 8. And then I can just mirror them because I already have the axis symmetry. So this would go left 1, left 1 more. This one I would need to count twice to the left, and then I need to count 2 more times to the left. So that'll be at negative 2, 8. So again, a vertical stretch is you take the original coordinates and you multiply the y values by whatever you have. So if it was a vertical compress, you would multiply the y values by the fraction that you have, the number less than 1. This next example, if I take off the numbers and leave the symbol, we're left with the square root, y is equal to the square root of x. So our transformations, the a value is still a positive 1. The h value is now different. So we have an h value of, it needs to be x minus a negative 5 to make that plus 5. So h is negative 5. The k value has turned into a negative 4. So this tells us the horizontal movement has gone left 5. And the vertical movement has gone down 4. These are our transformations. from our parent function, going to graph parent function of the square root of x, 0, 0, 1, 1, and 4, 2. For the transformations of this, I'm going to move all of these three coordinates left 5 and down 4. So this first one, 1, 2, 3, 4, 5 left, and then 1, 2, 3, 4 down first coordinate. Next coordinate, left 1, 2, 3, 4, 5, down 1, 2, 3, 4 coordinate. Next one, left 1, 2, 3, 4, 5, down 1, 2, 3, 4. So I only have these three coordinates, and it's always good to have a little bit more. What you want to do is go back to the original equation. Let's come up with a value to use. Certain x values you don't want to use because you want to take the square root of it. My next x value would be 0. 0 plus 5, cannot do the square root of that. 1. 1 plus 5 is 6, can't take the square root. 2. 2 plus 5 is 7, can't take the square root. 3. 3 plus 5 is 8, cannot take the square root. 4. 4 plus 5 is 9, I can take the square root. So we want to use 4 as our next x value. So 4 plus 5 is 9. The square root of 9 is 3. So it's going to be 3 minus 4, which is negative 1. So we plugged in the 4, we got out the negative 1. We inputted 4, we got an output of negative 1. So that is our coordinate. And we also had, the next one would have been on here, would have been 9, 3. So if I had started at 9, 3, and I went left 5 and down 4, we would have ended up at 4, negative 1. This last example, to take off all the numbers, leave the symbol, we have y is equal to x. The transformation occurring, the only thing that's different is it is a vertical, because your a value, let me write out, a value is equal to 3. It was already positive, but it's equal to 3. So that's a vertical stretch, because this is bigger than 1. It's a vertical stretch of 3. And again, it's vertical because it's multiplying the y values, not the x values. The parent function is going linear with a slope of 1 going through 0, 0. So what we're doing here is we are multiplying the y values by 3. So 0, 0 is 0 multiplied by 3 is still 0. 1, 1. 1 times 3 is 3, so it will become 1, 3. That's our new coordinate. Next one is 2, 2. So 2 times 3 is 6, so the new coordinate becomes 2, 6. And this is, if I look at the equation to just graph it, this is a slope of 3 and a y-intercept of 0. So 0, 0. Slope of 3 is up 3, right 1. Up 3, right 1. Did the exact same thing. So I could continue going down 3 and left 1. Down 3 and left 1. And just to check, this coordinate is at negative 1, negative 1. Negative 1 times 3 is negative 3. So negative 1, negative 3. This coordinate is at negative 2, negative 2. Negative 2 times 3 is negative 6. So we go to negative 2, negative 6. And that's where that's located. So the transformations are affecting the coordinates of the parent function, which is why you need to understand what the parent functions are, and you can still do this without the use of a calculator.